students, topic for the day is line coding. So line coding is a process that converts data which is in the form of binary digits into a baseband data signal. That means the data which is in the form of binary ones and zeros, we can convert it to a digital signal, as you can see in the diagram. It is also called a digital baseband modulation or digital baseband transmission. So line coding, there are many line coding techniques ranging in complexity from very basic unipolar schemes in which the presence or absence of voltage is used to represent a binary 1 or a binary 0 to highly sophisticated multi-level schemes in which different signal amplitudes are used. Now, line coding schemes can be broken into 5 major categories: unipolar, polar, bipolar, differential, and multi-level. We'll be looking at them one by one. Before that, the unipolar and polar and bipolar line coding schemes can be further categorized as either non-return to zero or return to zero, in short known as NRZ and RZ. Because we'll be shortly taking up all those schemes in which we would need the concept of these terms. So it is better to have an understanding of them right away. In a return to zero scheme, if a signal uses a positive or a negative voltage to represent a binary digit, the voltage must return to zero in the middle of the bit time. So it would be clear from this example. Say this is the clock and this is the data we want to transmit. Data is 0, 1, 0, 0, 1, 0, and so on. So our signal would be, for 0 it would be a low voltage like a 0. Here you can see a 0. So 0. In case of 1, it would be a positive voltage, as you can see from this. So then there is a 0, so there is a transition to the 0 voltage, or 0 voltage is representing a binary 0. Same here for another 0. Then there is a transition in case of 1. Then there is again a transition, downward transition to a 0 voltage to represent binary 0, and so on. So this is an example of NRZ, means non-return to 0. Now, return to 0 means for a 0, you can see you have shown it as a 0 voltage here, but in case of 1, you have shown a transition, upward transition, so a positive voltage represents a 1, but in the middle of the bit time, so this is the bit time. So in the middle of the bit time, it again comes back to 0 and then starts another transition or representation, which in this case is 0. Then there is a 0 again. Then there is a 1. You can see an upward transition and it then goes back to 0 during the bit time. So you can compare the two diagrams to have an idea of the difference between the two. So the first scheme, line coding scheme, we will be discussing is the unipolar NRZ. So unipolar is the NRZ. We just discussed that it would be a non-return to zero pattern. In a unipolar signaling scheme, all non-zero signaling elements have the same polarity. That means either they are all positive or they are all negative. The presence of a voltage pulse signifies a binary 1 and absence of a pulse signifies a binary 0. Let us see from the diagram. So for 0, 0 voltage represents a 0. 1, a positive voltage. 0 voltage represents a 0. Again 0 voltage represents a 0. Then there is a transition to 1, 1, which is the highest, a positive voltage, which represents a 1. Then there is a downward transition to 0 voltage representing a 0. Then an upward transition to a positive value representing 1, again 1, 0, and so on. So then there is unipolar but RZ. So here we'll be returning to 0 in the middle of the bit time. So 0, 0, is represented by 0 voltage. Then for 1 you will have a transition, but in the middle of the bit time you would again come down to 0. So return to 0, and then you would make the representation of the next bit, which is the 0. So 0, 0, then there is a 1 and the transition in between the bit time, as we already discussed. So then there is polar NRZ level. So it is also known as NRZL. So here binary 0 is represented by a positive voltage, but binary 1 is represented by a negative voltage. So this is your data. This is your data, and your signal would be for 0 it would be a positive. So you can see here 3 patterns. So positive, 0 and negative, 0 in between and negative beneath, and towards the upper side we have a positive signal. So to represent a 0, as suggested here, it is represented by positive voltage. Then there is a 0 here, 1 here represented by negative voltage, then 0 here represented by a positive, again positive to represent 0, then there is a 1, and so on. Then there is another technique that is known as polar NRZ but invert. In short, it is known as NRZI. Here the value of the bit is determined by the presence or absence of a transition from a positive voltage to a negative voltage and vice versa. In general, binary 0, no transition. So in case of binary 0, there would be no transition. In case of binary 1, there would be a transition. So let us see here. So 0, then there is a 1, so there would be a transition. There will be a transition, then there is a 0, no transition, then there is a 0, no transition, then there is a 1, there will be a transition. Transition means it would change from low to higher, high to low. Then there is 1, then there is 0, there will be no transition, then there is 1, there will be a transition, then there is 1, there will be a transition, 0, no transition, and so on. It is also known as differential code, as it makes the use of transitions rather than levels to signify logic values, right? So similarly we have polar RZ. It uses 3 signal levels. Logical 0 is represented, or binary 0 is represented by a negative value. Logic 1 or binary 1 is represented by a positive voltage. So in both cases the signal level returns to 0 halfway through the bit time, as you can see. So my data is 0, so 0 is represented by a negative voltage and it returns to the 0. As you can see, 0 is this middle line. 0 voltage is represented by this middle line. So whenever you are coming back to 0, it would come to this point. Similarly, from an upward transition, you will come back to this place. So during every bit time there is a transition midway. So if this is 0, this is 0 represented by a negative voltage, then it would come to 0 level. Then it would see what is the next bit. What is the next bit? Next bit is 1, so it would be a positive transition, but again coming back to the 0 level because it is an RZ scheme, right? Similarly, you would go on doing the same thing. Some sources refer to this line encoding scheme as bipolar RZ, right? So then there is bipolar AMI. It also uses 3 signaling levels. Bipolar alternate mark inversion, or AMI, uses alternate positive and negative voltages to represent binary 1, 0 voltage to represent binary 0. Right? So a 0 voltage would be representing what? A binary 0, and alternate positive and negative voltages would be used to represent a binary 1. So in here you can see 0, so 0, so it is represented by 0, 1 is represented by a positive transition or the positive value. So 0 by 0, 0 by 0, then there is an opposite. In case of this one, there is an opposite transition. That's why we said alternate positive and negative voltages. So zeros would be lying here are represented on this line, but all the ones would be alternating as far as the positive and negative voltages are concerned. So if there is one, this one represented by a positive voltage, this one would be represented by a negative voltage. Same for others. Then there is bipolar C2-ternary. It also uses 3 signaling, but it is exact opposite of what happens with AMI. That means alternate positive and negative voltages are used to represent binary 0, while the 0 voltage would represent binary 1. So it is absolutely opposite of what we saw in the previous slide. You can see it in the diagram also. So 0 is represented by a positive voltage. Then 1 would be lying on the 0 voltage line. In case of another 0, now we would be making the opposite transition of the previous one. The previous 0 was represented by a positive voltage. Rather, this 0 would be represented by a negative. This 0 would be represented by a positive again, and this 0 would be represented by negative voltage. So it is opposite of AMI. Then there is Manchester encoding. Binary here, binary 1 is represented by a positive pulse with a period of half a bit time followed by a negative pulse of the same duration. Binary 0 is represented by a negative pulse followed by a positive pulse. Right? So as you can see from the diagram, that 0 is represented by a negative voltage followed by transition to a positive voltage during the same bit time. So for this one, it is represented by a positive voltage but followed by a transition to a negative voltage but during the same bit time. Same for this, 0 is represented by a negative voltage but followed by a transition to a positive voltage during the same bit time, and the process would go on. Then there is differential Manchester encoding, in which for a binary 1 there is a transition at the beginning of the bit time, and for a binary 0, or to represent binary 0, there is no transition at the beginning of the bit period or bit time. So here you can see for a 0, 0 is going to be represented by a positive voltage followed by a transition, as we saw in case of Manchester encoding. Then there is a 1 at the beginning of, here you can see at the beginning of the bit time there is a transition from this to this. Now check here, in case of 0, the transition, there is no transition. As you can see, during the previous bit time the signal is represented, or it is here, and in case of a 0 there is no transition. So no transition at the beginning, then there is a transition. You can see in the second half of the bit time. Then there is a 0 and it retained the previous state or the level. So there is no transition at the beginning, then there is a transition in the middle of the bit time. Then the next one there, since in case of 1 there should be a transition at the beginning of the bit time, so here you can see the transition from this to this. And of course then there is this transition which is part of the Manchester encoding. Then here in case of this 0, the previous state is retained and there is no transition, and you can see it or check for other bits also. Then we have two different kinds of coding schemes. The first among which is the 2B1Q or 2 binary 1 quaternary encoding. In 2B1Q, a die bit means a pair of bits, is represented by 1 quaternary symbol. So before going ahead, let us see. So if the data, for example, is 00, which is a die bit, a couple of bits or a pair of bits, its output is, for example, shown by a voltage of or a value of -3. Similarly, for 0, 1, it would be a -1. For 1, 0, there would be a value of +3, which would be assigned. And for 1, 1, there's a value of +1. So as you already know, in case of binary, how many combinations are possible or patterns are possible when we use 2 bits. It is 2 raised power 2. 2 of binary, which is the base, and 2 is the number of bits. That is the exponent here. So 2 raised power 2 is 4. So the combination would be 0, 0, 0, 1, 1, 0 and 1, 1, which are assigned different values. So in this example, we have used the numbers +3, +1, -1 and -3 to represent pulse levels rather than the actual voltages. The table here pairs each die bit with the pulse level used to represent it. So this could be clearly seen from the diagram, a 0 and a 1. So it is a die bit, since we are talking about the die bit. So 0, 1 is, as you can see, 0, 1 is -1. So that is why you have put it, the signal level, denoted it right here, which represents -1. So then there is 0, 0, 0, 0 is -3. So you can see it here, -3. You have plotted it here. Similarly, for other values like 1, 0 and 1, 1 and so on. So you will have to simply check the bit pattern or die bit pattern, and the corresponding value could be represented, which could be seen from this table. Then there is 8B60, that means 8 binary and 6 ternary encoding. As you would have guessed, so would be kind of 8 combinations or 6 combinations involved in this case, as against the 1B, 2T. So this coding scheme uses 3-level pulse amplitude modulation to code a block of 8 binary digits onto a sequence of 6 signaling elements. So we have 6 signaling elements, and we would be having, or we would be combining 8 binary digits to represent those 6, or a combination of those 6 signals. So each signal element takes one of the 3 values, that is positive, negative or the 0, as you can see in this diagram, positive, 0 and negative. Each group encodes an 8-bit binary number, which can also be represented as a 2-digit hexadecimal number. You may be aware of the fact that we need 4 bits, that is 4 binary bits to represent a hexadecimal number, hexadecimal digit, we can say. So here you can see in the example that the binary 8-digit bit combination 0, 1, 0, 0, 1, 0 and 1, 1 is represented by a signal pattern like this. Same for this and same for this. Now one interesting thing is that to derive signal pattern to be used to represent each 8-digit bit pattern, lookup table must be used. So in case of 21BT, so it was easy to relate the output to the input because we had lesser number of combinations. But here, since there are many combinations that could be related, that could be used or derived, the lookup table must be used. The lookup table maps each. What is the function of the lookup table? It maps each digit binary, 8-digit binary number to the appropriate signal pattern. As you can see from this, it is also available on Tata McGraw-Hill's Access Engineering website if you want to check. So thank you.